Welcome back to Talk Tensors, everyone. We're the podcast that digs into the nuts and bolts of machine learning research.
And today, we've got a really interesting one. We're diving into a paper that looks at something pretty fundamental in image generation.
Absolutely. We're talking about how AI models create images from text or other prompts specifically, a technique called classifier guidance, and its more common successor, Classifier-Free Guidance, CFG.
Right, CFG. If you're working in generative models, CFG is, well, it's basically everywhere. It's kind of the standard toolkit for getting good results, for controlling the output based on conditions like text or class labels.
It really is a staple. You see it referenced constantly. But here's the kicker, and what this paper really focuses on.
Yeah.
Despite how crucial CFG is for getting those amazing high-quality images, truly understanding why it works so well, that's been a bit less clear, hasn't it?
Exactly. It's one of those things that works incredibly well in practice, but the deep theoretical grounding, or maybe a complete intuitive picture, has been somewhat lacking.
So that's our mission for this deep dive. We want to unpack this paper that offers a fresh look at CFG, mainly by digging back into its roots, the original classifier guidance.
Yeah, they do this careful empirical study, looking at the classifier's role in that older method to shed light on both.
And the core idea they put forward is fascinating. They suggest both methods, the old one and the new CFG work, by essentially pushing the image generation process away from certain tricky areas.
They call them decision boundaries. These are like the fuzzy zones where the model might get confused between different categories or conditions where the information is complex.
Makes sense. Avoid the confusing parts.
Pretty much. And building on that insight, they actually propose something new, a kind of post-processing step.
Oh, interesting. Like a cleanup crew.
Sort of, yeah, using something called flow matching. The idea is to improve the generated images, especially fixing issues that pop up around those difficult decision boundaries.
Okay, sounds promising. Let's maybe rewind a little first. For context, what's the basic challenge with conditional generation using these diffusion models? What were people trying to do?
So the fundamental goal is sampling data, like images, let's call them X0, but not just any image. You want an image that matches a specific condition, C.
Right. C could be text, like a cat wearing a hat, or just a class label, like dog.
Exactly. You want the model, let's say PXC, to learn that mapping from condition C to plausible images X0.
And diffusion models came along as a powerful way to do this. What's the core concept there? Adding noise and reversing it.
Yeah, that's the essence. You take a real image, add noise gradually over many steps until it's just static. That's the forward process.
Okay.
Then the model learns the reverse process. Starting from noise, step by step, it removes the noise to generate a clean image. It's a Markov chain, technically.
And the conditioning, the C, comes in during that reverse denoising part.
Precisely. The model learns to predict the noise that needs to be removed at each step, often written as SOIN. And this prediction is guided by the condition C.
So it's not just removing any noise, but removing it in a way that leads to, say, a cat, if the condition is cat.
Exactly. It's linked to ideas like score matching, estimating the gradient, basically learning the direction and data space to move towards realistic and condition matching samples.
Got it. Okay, so that's the foundation. Now, this paper looks back at classifier guidance first. How did that approach work?
Right. Classifier guidance was an earlier method. It kind of broke the problem down. You had two pieces.
Two models.
Yeah. First, an unconditional diffusion model. It just learns to denoise, to make any image look real regardless of class. Let's call it P, XT plus 1.
Okay, a general image generator.
And second, you had a separate classifier, PXT. This classifier was trained to look at a noisy image, XET, and predict its class C.
Ah, okay. So one makes it look real, the other makes it look like the right class.
Exactly. During generation, you'd combine the guidance signals, the gradients from both. The diffusion model pushes towards realism. The classifier pushes towards the target class C.
Seems logical. But you mentioned limitations, and this paper points out a key assumption.
Yes, a crucial assumption in the original derivation. It basically assumed that adding noise to an image, the forward process, happens the same way, whether you know the class condition or not.
That sounds subtle. You mean the noise addition process itself?
Yeah. They denote the conditional forward process as QXT plus 2XTC, and the unconditional one as QXT plus first is T. The assumption was that these two behave identically.
And this paper says they don't.
Their experiments, starting with simple 1D data, suggest that assumption doesn't really hold up in practice.
How did they show that? What did they see in 1D?
They compared a standard conditional model, trained directly with labels to the classifier guidance setup. Unconditional model plus classifier. The paths the generation took, the trajectories from noise to data were different.
Different shape.
Yeah. The classifier guidance paths looked, well, distorted, pushed away from the areas where the classifier would be uncertain the decision boundaries between the 1D classes.
And they mentioned the guidance scale, right? The W parameter that dials up the classifier's influence.
Right. And they found that cranking up that guidance scale made the trajectory differences even more pronounced.
So more guidance means push harder away from those uncertain zones.
Exactly. It really highlights that the classifier isn't just a small nudge. Its characteristics, its confidence levels dominate the generation process in classifier guidance. They even showed different classifiers created totally different paths with the same base diffusion model.
Wow. Okay. So the takeaway is classifier guidance works by actively avoiding the classifier's don't know regions.
That's the core insight they present. Steer clear of the decision boundaries where the classifier is uncertain. High guidance forces samples into high confidence zones.
Which brings us to Classifier-Free Guidance, CFG, the more modern approach. How did that try to fix the issues with needing a separate classifier?
CFG was clever. It gets rid of the separate classifier by training just one model. But during training, sometimes you randomly drop the conditioning information C.
So the model sees examples with the condition and sometimes without it.
Exactly. This forces the single model to learn both how to generate conditionally and unconditionally punct. It has to handle both scenarios.
And how does that connect back mathematically? Does it end up doing something similar to classifier guidance?
Yes, that's what the paper shows. Using Bayes' rule, you can decompose the math. The effect of guidance in CFG ends up looking like a combination of the model's conditional prediction and its unconditional prediction.
So even without a separate classifier, it's explicitly calculating something analogous, like the difference between knowing the condition and not knowing it.
Precisely. It mathematically relates back. And their 1D experiments suggest CFG behaves similarly too.
Also pushing away from decision boundaries.
That's what they found, yes. It also seems to steer trajectories away from those boundaries. They did note it might be even more sensitive to the guidance scale, perhaps because the conditional and unconditional parts are tied together in one network.
Okay, so this similar behavior leads to their hypothesis. If we can improve classifier guidance, maybe those ideas also apply to CFG.
That seems to be the thinking, which sets the stage for their proposed post-processing step.
Right, the flow matching idea. Let's unpack that. What is flow matching, basically?
Flow matching is a technique, relatively recent, for learning to transform one data distribution into another. You learn a vector field, like a velocity field, that tells you how to continuously move points from distribution A to distribution B.
Okay, like learning a current that pushes samples around.
Yeah, that's a good analogy. Here they want to learn a flow that pushes samples from the diffusion model's generated distribution towards the real data distribution.
So it's a correction step applied after the main generation?
Exactly. You generate an image with your diffusion model using classifier guidance or CFG, and then you apply this learned flow to refine it, to make it look more like a real image.
And they use a specific training objective for this flow involving nearest neighbors.
Right. This is quite clever. When training the flow, they take a generated sample, find its closest neighbor or neighbors in the real data set.
Its nearest twin in the real data.
Kind of, yeah. And the goal of the flow is to minimize the distance between the generated sample and that real nearest neighbor.
Why the nearest neighbor? What's the logic?
The beauty is, if your generated image is already really good, really close to a real image, the distance to its nearest neighbor is tiny.
So the flow learns, basically, don't touch this one, it's fine.
Exactly. A very small learning signal. Right. But if you generate a low quality image, maybe one messed up near a decision boundary, it's going to be far from any real image.
So the distance is large, and the flow gets a strong signal to push that bad sample towards the nearest good example.
Precisely. It focuses the correction effort on the worst offenders, the samples that are far from the true data manifold.
That's smart, self-prioritizing correction.
Yeah. And to avoid getting stuck, they actually suggest finding the top K nearest neighbors and randomly picking one as the target during each training step. Adds a bit of robustness.
So the full process is generate with diffusion, then refine with this learned flow using an ODE solver.
That's the two-step process, yes. Generate, then solve the ODE guided by the learned flow, the velocity field, to push the sample closer to the real data.
They mentioned this relates to auto guidance, but call it cascading. What's the difference there?
Auto-guidance usually involves using a model to guide itself, maybe a degraded version guiding a full version. This is different. It's a post-hop step.
Like adding another stage in a pipeline.
Exactly, a cascade. You take the output of one model, the diffusion generator, and feed it into another, the flow refiner. It explicitly acknowledges the pre-trained model might not be perfect and adds a dedicated step to fix its distributional errors.
And a potential side benefit is maybe less fiddling with the guidance scale W.
That's a hope, yeah. If the post-processing can clean up outputs across different guidance levels, maybe you don't need to spend as much time searching for that one perfect W.
Okay, theory sounds good. How did they test this? They started with that 2D fractal data set again.
They did. The fractal data let them control how tangled up the classes were, the entanglement of the decision boundaries.
And did the post-processing help?
Big time. The results, visually and quantitatively, showed significant improvements for both classifier guidance and CFG across different guidance scales, especially as expected around those tricky class boundaries.
Nice. What about real images, MNIST?
Moved on to MNIST next.
Yeah.
Same story, basically. The post-processing helped align the generated digits better with the actual digit classes for both guidance types. They even had PCA plots showing the distribution of generated digits getting visibly closer to the real MNIST distribution after refinement.
That's pretty convincing. And what was this one-for-all scales idea?
Yeah, that was interesting. They tried training one post-processing flow model using samples generated with a mix of different guidance scales.
Instead of one flow per scale.
Right. And they found this single one-for-all model performed surprisingly well, sometimes even matching or beating flows trained for specific scales.
Suggesting the types of errors are similar across scales.
It seems to hint at that, yeah. That there might be common failure modes that a single refiner can learn to fix, which could be very practical.
Definitely. Then they tackled CFAR-10, a harder data set.
Yep, CFAR-10, using a flow matching model as the base generator first. One finding was that CFAR-10 seems to have relatively low entanglement. The classes are fairly separate.
So less boundary confusion, maybe.
Potentially. But even so, the post-processing still improved quality, especially at higher guidance scales. They also did an interesting test on how to find nearest neighbors.
Raw pixels versus
Features from a big vision model, Dino V2. And using those learned Dino V2 features work best for finding good neighbors for the flow training.
Okay. Any downsides? Did it hurt diversity?
They noticed a slight dip in diversity, measured by FID score, at very low guidance scales after post-processing. But they found using more nearest neighbors, larger K, helped mitigate that.
Right. Don't just pull everything towards the single closest image.
Exactly. Given a few options.
And they also tested with a different base model on CFAR-10, right? EDM.
Yes. Elucidated diffusion models, another strong baseline. The results held up, confirmed the low entanglement idea for CFAR-10, and showed the post-processing stabilized performance across guidance scales. Interestingly, it even seemed to boost diversity at high guidance scales with EDM.
Oh, that's unexpected, but good.
Yeah, it suggests the approach is pretty robust and generally applicable, not just tied to one specific type of diffusion model.
Okay, so let's try and wrap up the core message of this paper then.
I think the main takeaway is this reframing. Both classifier guidance and CFG seem to work, at least in part, by pushing away from these difficult decision boundaries in the data space.
Steering clear of ambiguity.
Right. And recognizing that this steering can sometimes lead to its own problems near those boundaries, they proposed this flow matching post-processing step as a way to clean things up.
A targeted refinement stage.
Exactly. And they showed with experiments on various data sets that it can genuinely improve generation quality, particularly in those challenging regions.
It's a really neat contribution, tying together the analysis of guidance with a practical improving method.
Agreed. It offers both insight and a potentially useful tool.
Fantastic. For our listeners, if you want the full mathematical treatment and all the experimental details, definitely check out the paper linked in our show notes. It's worth the read.
Absolutely.
Now, as always on Talk Tensors, let's shift gears into our novel notions segment. Time to speculate a bit based on what we've just discussed.
My favorite part. Where do we go from here? This focus on classifiers and boundaries, plus the post-processing. It definitely sparks some ideas.
All right, let's hear notion number one.
Okay, so the paper talks about guidance pushing away from boundaries, right?
Mm-hmm.
What if we could make that push dynamic? Adjust the guidance strengths during generation?
How would that work? Like turn the guidance dial up and down mid-synthesis?
Kind of, yeah. Imagine you could estimate maybe with a small helper network, how close your current noisy sample is to a decision boundary.
Okay, a boundary proximity detector.
Right. Then connect that to the paper's finding. The obvious thing is, if you're getting close to a boundary, crank up the guidance strength temporarily.
Give it a stronger push away from the danger zone.
Exactly. Ensure clear separation. But here's the less obvious flip side.
Go on.
What if you detect you're far away from any boundary? Maybe then you could actually reduce the guidance strength.
Why would you do that?
Well, if you're in a safe region, far from confusion, maybe you don't need such strong guidance. Easing off could allow for more diversity, more variation within the class, without risking misclassification.
Ah, so it's an adaptive trade-off between fidelity, staying on target, and diversity, exploring variation.
Precisely. A system that could automatically modulate guidance based on boundary proximity. It could potentially find that sweet spot without needing us to manually tune one global W value.
That could be huge, especially for tricky data sets with complex class overlaps. Where have we seen related ideas before?
There's been some work on adaptive guidance, but this boundary-centric approach feels more targeted, more grounded in the mechanism discussed in the paper.
Any overlooked angles to this?
Maybe personalization. Could you tune this dynamic adjustment based on whether a user wants photorealism versus more creative outputs, bias it towards stronger pushes or more relaxed exploration?
Interesting. Feasibility-wise, what are the chances?
I'd say the tech for boundary detection and adaptive control is getting there, so feasibility is probably high. Whether it gives major quality boosts over static guidance, maybe medium probability, depends a lot on the data set and how well you can estimate that boundary proximity.
Okay, compelling idea. What's your second novel notion?
Okay, sticking with the post-processing idea, the paper used a general flow network to push generated samples towards any nearest real neighbor.
Right, a general refinement.
What if we made the refinement network specialized? What if we trained flow networks that are specifically conditioned on the boundary itself?
Flow networks that know about the boundaries? How?
You'd need a way to represent or predict the boundary location or characteristics near the sample being refined. But if you could do that, the flow network could learn corrections tailored specifically for boundary artifacts.
Like a specialist repair tool just for those regions.
Exactly. Instead of a general hammer, you use a fine, detailed chisel right where it's needed. The obvious benefit is potentially more efficient and targeted correction. Might need smaller networks, less data.
Makes sense. What's the less obvious potential?
Maybe these boundary condition flows could learn not just to fix errors, but to intelligently shape the boundary. Like, learn to make generated boundaries sharper or smoother, or add fine details along the boundary that are characteristic of the real data's class separation.
Whoa, like hallucinating plausible boundary detail.
Could be, especially in domains where boundary fidelity is critical.
Like medical imaging, segmenting tumors or tissues.
Perfect example. If you're generating synthetic medical data or using diffusion for segmentation tasks, having a post-processor that really understands and refines boundaries could be incredibly valuable.
What are the hurdles here? How likely is this?
Conditioning the flow effectively on boundary information seems like the main challenge. So feasibility, maybe medium, likelihood of it beating general post-processing, also probably medium, depends heavily on whether that boundary-specific information provides enough leverage. But for certain applications, the potential payoff seems high.
Fascinating stuff. Definitely gives us a lot to think about beyond the paper itself.
That's cool.
Okay, well, as we always say, these novel notions are just us thinking out loud, purely speculative, designed to get those research gears turning.
Absolutely. For the solid findings, go read the paper.
Couldn't agree more. Thanks again for joining us on Talk Tensors for this deep dive. We hope you found it insightful.
Always a pleasure.
We'll catch you next time with more from the cutting edge of machine learning.